This is part 2 of lesson 12.3, learning about geometric sequences in series. For this first example, now we're asked to write a rule for the nth term of a geometric sequence given a particular term in the sequence and given the common ratio. Now if you remember from part 1 of the lesson, we said that to write a rule for the nth term of a geometric sequence, we need the first term and the common ratio raised to the n minus 1 power. So I need to know those two things, first term, common ratio. In this case, I'm given the common ratio of 3, but I don't know the first term. Now instead, I'm given a different term within that sequence. So we're going to use the algebra trick we talked about in the last lesson, which is plug stuff in. So in this case, I know that the common ratio is 3. I'll go ahead and put a 3 where r is, raised to the n minus 1. And actually, again, remember we don't know what the first term is. So I'll put a sub 1 times, in parentheses, the 3 that I did know. On the other side, now the nth term and n up there. I know that the fifth term in this sequence is 54. So I'm going to put 54 as the result, and I'm going to put 5 in the exponent for n. So 5 minus 1 is my exponent up there. Now it's my job to solve for a sub 1, the first term. Well, evaluating this expression, 3 to the 4th power is going to be 81. I take 81, which is what this expression was equal to, times a sub 1, and that equals 54. Well, now to solve for a sub 1, I'm going to go ahead and divide by 81 on both sides. And 54 divided by 81 is going to simplify down to 2/3. So I know my first term. I knew my common ratio from before. I'm going to go ahead and write my rule right here. The rule for this sequence is a sub n is equal to 2/3 the first term times 3 the ratio raised to the n minus 1 power. There's my rule for this particular geometric sequence. Now the second part says graph the first 5 terms of the sequence. In the assignment, if graphing is part of the directions, please ignore it. I just want to show you what this graph would look like because I think you'll recognize this graph from things that we've learned in the past. So if I were to graph the terms of this sequence, I'm going to start, I know they're all positive at the moment, so I'm going to go ahead and put down on my x-axis 0 to 5. And then I'm going to put in, let's see, when I plug in 5, the fifth term was 54, right? So I'm going to put 50 up here at the top and then kind of break it up accordingly, 10, 20, 30, 40. Now at each particular point I'm going to evaluate by plugging in one of these numbers. So if I plug in 1, 1 minus 1 is 0, 3 to the 0 is 1, 1 times 2/3 is 2/3. So when I plug in 1 I get 2/3, a number that's pretty low to the bottom. When I plug in 2, 2 minus 1 is 1, 3 to the first is 3, 3 times 2/3 is 2. Still pretty low as far as this scaled graph is concerned. Now I plug in 3, 3 minus 1 is 2, 3 squared is 9, and 9 times 2/3 is going to be 6. Yeah, I'm getting a little bit higher, but not much. Now watch what happens here. I plug in 4. 4 minus 1 is 3. 3 cubed is 27. 27 times 2/3, well that's going to be 18. So all of a sudden there's a little bit bigger of a jump. Okay? I think maybe you can see where this is going. Now when I plug in 5, I already know that I'm supposed to get 54 from earlier, so I'm going to go ahead and put my point up here. Now as you look at these dots, first of all it's a sequence, so we should not connect them. They're just dots. There's nothing in between these integer input values. But if you notice the shape that this would take if we were to connect it, this matches up with the exponential growth functions that we looked at in chapter 7. And it should, because this is an exponential function and its base is greater than 1. So it should make sense as we graph it. Now the second part of this page of the notes, again we're asked to write a rule for the nth term of a geometric sequence. But this time we're given different pieces of information. So, if you remember the things that we need to know. We need to know the first term and the common ratio. In this case, I know 2 terms, but I don't know the first term, and I don't know the common ratio. So what I have to do is I have to do a little bit of work to find that. Now, in an arithmetic sequence, what we did is we used basically the slope formula to find the difference between, here was the value at this point, here's the value of this term. Well, subtract the 2 and divide it by the difference between the 2 terms. Okay, sort of like slope. And we were able to do that because an arithmetic sequence matched a linear equation. Now in this case, I am multiplying over and over and over again. That's why I have that exponential curve graph. Well, because I'm multiplying over and over again, instead of subtracting like we did, well, we're going to use the inverse of multiplication, which is division. So, to find R, the ratio, we're going to take the second output, which is 405, divided by the output, the other output that we're given, which is 45. Okay? So this is the fifth term, and this is the third term. Well, the difference between these two, if I take 405 divided by 45, we end up with 9. Okay? So somehow I went, and if you kind of picture this, I went from 45, and then there was another term, and then there was 405. And remember, we're multiplying by something over and over again. So I multiply by I don't know what, and I multiply by the same thing, and it turns into 405. Well, 45 to 405, that's, they're not a ratio of 9. So I multiplied by 9 to get from here to here. What would I multiply by if there were a step in between those two? Well, think about that. I'm multiplying by something twice and it equals 9. And it's the same thing over and over again. So if it's repeated multiplication, what I could do here is to find out what this common ratio is I'm going to take the square root of that number. Now, I'm able to take the square root. Now here's the trick. It's a square root because these terms are 2 terms apart. This is the fifth term and this is the third term. They're 2 terms apart, so I'm going to take the square root of that number, which in this case is either positive or negative 3. Okay? If these had happened to be the third root and the seventh root, for instance, 4 terms apart, the third term and the seventh term, they'd be 4 terms apart. Well, then I'd be taking the fourth root of whatever number I might happen to get. Okay? So you're going to take that particular root based on how many terms they are apart. 2 terms means square root. Now, I've got either positive or negative 3 as my common ratio. Okay? So that's what we're going with. But we still need to know what the first term is. So one way you can think about it is I could just sort of back up. I know the third term is 45. Let's back up to the second term and the first term. If 3 or negative 3 is my common ratio, let's imagine dividing 45 by 3. Well, if I divide 45 by 3 or negative 3, I'm going to have either positive or negative 15. And then if I divide that by positive or negative 3, I'm going to end up with, if this is positive, this is going to have to be positive. Divide 15 by 3, we're going to have 5 as our initial term. So it's just a matter of working backwards to figure out what the first term is. Now that I know the first term and I know the common ratio, I'm going to go ahead and write my rule. My rule is equal to the first term, 5, times my common ratio. I'll put 3 to the n minus 1, and I'm also going to put this because this is also an option because, it could be 3 or negative 3 because we weren't told if these terms were negative or not. Okay? So either one of these would be acceptable. Now, to make sure that you're not stumped by ones that aren't necessarily square roots, I want to give you another example that I just, kind of making up. So let's say I'm told that the second term in a sequence is negative 14, and let's go with the fifth term in the sequence is equal to 112. Okay? And it's a geometric sequence. So if it's a geometric sequence, I'm going to start by trying to find R. Well, like we did before, we're going to divide. 112 divided by negative 14, that happens to be negative 8. Now, there's in between the second term and the fifth term, that's a difference of 3 terms. Because it's a difference of 3 terms, I'm going to take the cube root of that ratio. See how that works? So the cube root of negative 8 is negative 2. So negative 2 is my common ratio. As I start to fill things in, here's my answer, a sub n equals, I know that negative 2 is going to be there raised to the n minus 1 power. Now the thing I still have to figure out is what the first term is. Well, the first term is equal to, let's see, well, I had the second term, right? So let's back up. In order to get negative 14, let's say if I were to back up, I'm going to divide by that common ratio of negative 2. Negative 14 divided by negative 2 would be positive 7. So 7 is the first term in my ratio. So 7 times negative 2 to the n minus 1 power would be my rule. That's the end of part 2 of the lesson.